Welcome back to the deep dive. If you've ever felt like security in the cloud is less about firewalls and more about answering that one eternal question, who can do what, then you are definitely in the right place.
That's a perfect way to put it.
Today, we're strapping in for what is really the absolute core of cloud architecture, identity and access management, or IAM, and we're focusing specifically on Google Cloud Platform.
That's the perfect framing. IAM in GCP isn't just, a feature you configure once and forget about. It is the definitive cornerstone of your entire security posture.
Right.
Get this right, and you minimize your exposure in a huge way. Get it wrong, and all the advanced networking and encryption in the world can't save your infrastructure, your data, or your apps. It's a gatekeeper.
And the weakest link if you mismanage it.
Exactly.
So our mission for this deep dive is to move past the 101 concepts and really establish a security architecture that is truly robust. We want a setup that minimizes breach risk by enforcing the most sophisticated techniques out there.
Yeah, think of this as the shortcut. A practical shortcut to a security posture that can survive an audit.
Yeah.
And maybe more importantly, a sustained attack.
Okay, so to do that, we've distilled everything down into 8 foundational pillars.
That's right. These are the principles that take your setup from just a basic configuration to, enterprise level maturity. We're going to dissect the principle of least privilege, the need for centralized identity management, regular auditing.
The really tricky stuff like service accounts and workload identity federation.
Oh, yeah. And then the organizational pieces.
Mhm.
Separation of duties, the non-negotiable layer of multi-factor authentication, the surgical precision of IAM conditions, and finally, how the GCP hierarchy and its inheritance model dictates every single permission flow.
Okay, let's unpack this immediately. Let's start with that first foundational concept that really everything else is built on, the principle of least privilege, or POLLP. It sounds deceptively simple, but what does it actually mean when we're applying it in a complex, multi-project GCP environment?
POLP is the cardinal rule, and its complexity isn't in the idea, it's in the discipline required to enforce it. It dictates that every single principle, so every human user, every service account, every application, must only be granted the absolute minimum set of permissions needed to do its job.
And nothing more.
And nothing more. It's all about limiting access based on necessity, not convenience or what they might need in the future.
That brings us straight to the danger zone then. Why is granting those broad, convenient roles the kind everyone defaults to when they're in a hurry? Why is that so risky?
It creates a massive and totally unnecessary blast radius.
The blast radius, okay?
Yeah, just imagine your primary security risk.
Hmm.
An account credential gets compromised. Maybe an API key leak, maybe a successful phish against a developer.
Right.
Now, if that compromised account was only granted permission to, say, view BigQuery metadata, what can the attacker do? They can only see your table names. The blast radius is tiny, it's contained.
But if that same account holds a broad role, like project editor or, and we've all seen it, project owner,
The attacker essentially has the keys to the kingdom. They can delete production VMs, they can disable firewall rules, spin up crypto mining clusters, pull petabytes of sensitive data from cloud storage.
they could even lock you out of your own project.
They can revoke the access of the legitimate administrators, locking you out entirely. The wider the role, the larger the potential devastation. That's the blast radius.
And we see this failure all the time in the real world. The classic counterexample is giving a new employee the owner role on a production project, just in case they need to configure something.
It feels efficient, but it's a time bomb. It really
A
is.
ticking time bomb.
That just-in-case mindset is pure technical debt.
Mm.
To enforce POLP with any kind of precision, you absolutely have to understand the official role selection hierarchy in GCP. This is where a lot of the mistakes start.
Okay, so let's break that down. Those 3 types of roles.
Right, so at the top, at the highest risk level, you have the primitive roles: owner, editor, and viewer.
The big 3.
The big 3, they're broad, they're legacy roles. And the strict absolute rule for a secure GCP architecture is you avoid these entirely in any production or sensitive environment. They just grant way too much power across too many services.
So if we're avoiding primitives, what should be our go-to, our default?
You move down to the predefined roles. This is your sweet spot, really. These are roles that are defined and managed by Google, and they offer a much more granular level of control that's tied to specific services.
So things like compute instance admin v1 or storage object creator.
Exactly. If a predefined role exists that satisfies the exact minimal requirement for a job, you use it. It also makes maintenance easier because Google is managing the permissions behind that role for you.
But sometimes even those predefined roles are a little too generous, and that's when we get to that third tier, custom roles.
Precisely. Custom roles should only be your last resort. You only use them when a predefined role is demonstrably, provably too broad.
Yeah.
The catch here is that creating custom roles adds administrative overhead.
Right, now you own it. You have to maintain it.
You are now responsible for defining, documenting, and maintaining that exact permissions list. So you only do it when the scenario is extremely specific.
Can you give us a concrete example? Where is the complexity of a custom role actually justified over just using a slightly too broad, predefined role?
Okay, let's say you have an operations team. Their only job is system hygiene. They need to be able to reboot or stop a VM instance. But under no circumstances should they be able to delete that instance or, say, change its disk.
Okay.
Now, if the existing compute instance admin role grants both stop, start, and delete permissions, and there's no other predefined role that fits, then you have to create a custom role, one that explicitly includes compute.instances.stop and compute.instances.start.
While explicitly excluding compute.instances.delete.
Exactly. That's the only way to achieve true least privilege. And in that case, the administrative burden is absolutely justified by the security you gain.
Let's try to illustrate PoleLP with a few of those real-world shifts we need to make. Let's start with cloud storage. That's a place where permissions are commonly overgranted.
A classic failure is assigning storage admin. It's so common. That role lets you do everything: create buckets, delete buckets, change global policies, and read and write all the data.
Total control.
Total control. Instead, if your data analyst only needs to read objects for analysis, what do they get? They get Storage Object Viewer. If your nightly ETL script just needs to upload reports, it gets the highly restricted Storage Object Creator.
So you're segmenting responsibilities not just by the user, but by the specific action they need to take.
It's surgical precision. That's the goal.
And what about for Compute Engine, where developers are often working?
You never, ever start with Compute Admin. If a developer needs to manage the lifecycle of virtual machines, starting, stopping, patching them, you assign Compute Instance Admin, V1. If they're just debugging or monitoring and shouldn't be making changes, they drop down to Compute Viewer.
And you can get even more granular than that.
Oh, absolutely. If they only need to manage, say, firewall rules, they get the Compute Security Admin role. That ensures they can't even touch the VMs themselves. We are slicing that big admin pie into its smallest functional components.
Okay, so now that we've established how to limit access for individuals, let's transition into Section 2, managing the identities themselves, especially that huge potential attack surface. Non-human access.
Exactly. Because if you get the identities wrong, PolePL doesn't mean a thing.
The sources all strongly emphasize centralized identity management. Why is it so critical to maintain consistency from a single source of truth?
Because the alternative is just. It's a recipe for administrative chaos and massive security gaps. Think about that hypothetical scenario we always see. A company manages accounts locally across, say, 10 different GCP projects.
Okay.
An employee leaves. The admin team has to manually go into all 10 of those projects and remember to revoke their access. What happens? Inevitably, 1 or 2 projects are forgotten.
And you're left with these dormant, highly privileged accounts just sitting there.
Indefinitely. Accessible indefinitely. Centralization completely eliminates that human failure point.
So how do we achieve that consistency, especially for bigger companies that are already relying on on-prem identity systems like Active Directory?
The foundational tool for that hybrid environment is Google Cloud Directory Sync, or GCDS. This tool isn't just about importing users once. It continuously synchronizes your on-prem Active Directory, or LDAP structure, your users, your groups, with Google Cloud Identity.
The magic is the consistency, right? The speed.
It's the immediate consistency. If a user is disabled in AD at 9:01 a.m., GCDS ensures that suspension is mirrored in Google Cloud Identity, and by extension, their GCP access is revoked almost instantly.
So once GCDS establishes that synchronized identity layer, what is Google Cloud Identity itself responsible for?
Cloud Identity is Google's identity as a service, or IDEA. That's where you enforce the global security policies that apply to every single human user you've synced.
Things like MFA mandates and password rules? Exactly. Mandating multi-factor authentication, setting organization-wide password complexity rules, establishing session lengths. It gives you a single policy enforcement point that covers your entire Google Cloud footprint.
Now let's tackle that major attack vector that isn't human. Service accounts. These are the digital workers of the cloud.
That's a good way to think of them.
Mhm.
They're non-human principles used exclusively by applications, VMs, Kubernetes pods, automated pipelines, you name it. They're essential because they let your automation authenticate to GCP services without using human credentials or hard-coded passwords.
And what's the most secure way to actually use a service account?
Attaching it directly to a resource like a Compute Engine VM or a Kubernetes pod. By attaching a service account, say, one with BigQuery data editor permissions, the application running on that VM automatically inherits that identity.
So it authenticates using the VM's metadata.
Exactly, and this is the key. No credentials ever leave the Google Trust boundary. There are no keys stored on the disk. But this brings us to the elephant in the room, the major security risk that plagues so many cloud environments. The problem of long-lived service account keys. The dreaded downloaded JSON file.
This is a massive vulnerability,
Yeah.
and the sources all stress its elimination. When you create a service account key, you download this long-lived JSON file. If that file is accidentally committed to source control, pushed to a public GitHub repo, or even just left on a desktop,
It grants full perpetual access to whatever that service account can do.
full perpetual access. The key doesn't respect centralization, it doesn't expire, and is so easily exploitable.
So how do mature organizations, especially those operating in hybrid or multi-cloud setups, get rid of this static key problem entirely? What is the secure, the exam-backed solution?
The answer is absolutely Workload Identity Federation, WIIF. This is the modern keyless approach. It completely removes the need to generate and manage those dangerous, long-lived service account keys for any of your external workloads.
That sounds great in theory. But let's get into the mechanics. How does WIFE actually work when an external entity, say, an application in AWS or in an on-prem data center, needs to access GCP resources? What's the trust model?
It relies on established industry standards, mostly OpenID Connect or OIDC. So first you define a workload identity pool in GCP. This is basically the point where Google says, okay, I will trust identities coming from this external source.
You're establishing a relationship.
You're establishing a trust relationship. You tell GCP to accept identity tokens issued by your external identity provider, like an AWS role or an on-prem IDP.
So the external application authenticates using its own local credentials first, and then what happens?
The application presents its external identity token, its AWS identity, for example, to GCP's secure token service. GCP validates that token against the trust relationship you defined in the identity pool. If it's valid, Google's secure token service then exchanges that external credential for a short-lived GCP token.
And that short-lived nature of the token, that's the whole security advantage, right?
Precisely. That token typically lasts only an hour, sometimes even less. If that short-lived token is somehow compromised, its utility is gone within minutes. Crucially, the external service never, ever has to manage or protect a long-lived static key.
So when the token expires, it just has to re-authenticate.
It re-authenticates and gets a fresh, temporary token. This mechanism, rooted in OIDC, is the gold standard for secure cross-platform access.
Okay, here's a challenge question that often comes up. If WonderWife is the gold standard, why do service account keys even still exist? Aren't we making setup overly complicated for smaller teams who just need a quick connection?
That's a fair point, and it really comes down to legacy systems and complexity trade-offs. Keys still exist for backward compatibility, especially with older systems that just don't support modern OIDC Federation protocols.
So it's a necessary evil for some.
For some, yes. And WIFE does add complexity. You have to configure an identity pool and a provider. But for any mission-critical or production environment, that initial setup cost is dwarfed by the massive security gain of eliminating perpetual key exposure. You're basically buying security insurance.
And the sources strongly advocate for forcing WIFE use organization-wide, which I'm guessing we'll touch on later with organization policies.
We will, absolutely.
That makes the transition to Section 3 pretty logical. We've defined and secured the identities. Now let's layer on some organizational and human process controls, starting with separation of duties, or SOD.
Separation of duties is really the formalization of that old phrase, trust but verify. It's an organizational philosophy and a control mechanism designed to prevent any single individual or entity from having end-to-end control over a critical or sensitive process.
It forces a check and balance system.
Exactly.
Give us a detailed example of where the lack of SOD could lead to, say, a catastrophic financial failure.
Okay, think about financial reporting and infrastructure spending. If one person holds both the billing account administrator role and the project creator role, they have complete autonomy.
That sounds dangerous.
It is. They can spin up massive, expensive projects, maybe for personal gain or just an accidental misconfiguration, and then they could hide or destroy the billing records. This could lead to millions in unchecked spending. SODA dictates that financial oversight, the billing admin, must be separate from the technical deployment authority, the project creator.
And in the software development lifecycle, the SDLC, where is OSE most critical?
It's the wall between development and production. It have to be. Developers should be able to write and test code in staging, but they must not have the authority to deploy that code directly into the production environment.
So you're separating the code creation role from the production deployment role.
Exactly. That separation ensures that your mandatory gates, automated testing, security scans, peer review are always enforced before the operational team takes ownership of the deployment. It massively improves stability and compliance.
That counterexample we talked about earlier, giving one person both owner status and sole approval for firewall changes, that seems to combine all of those risks into one single point of failure.
It is the ultimate failure point. That one person controls the entire digital kingdom and the entire security perimeter at the same time. If their account is compromised, the attacker can breach the system, modify firewall rules to let themselves in, exfiltrate data, and then delete the logs and resources to cover their tracks.
So what's the right way?
SEDU mandates that the authority to modify the firewall should reside with a dedicated compute security admin group, often requiring a two-person review, and that group must be separate from the team that manages the day-to-day operation of the VMs.
Let's move to our second layer in this section, multi-factor authentication, MFA. For mature organizations, this is just table stakes. But where should we be mandating it without any exceptions?
MFA has to be universally mandated for every single human user synchronized via cloud identity. Full stop. But we have to put an extra layer of requirement on all the highly privileged accounts.
So anyone with an owner role or admin roles at the org level.
Anyone with owner admin roles across the organization or folders, or any role that grants the ability to modify IAM policies themselves, they must have the strongest possible MFA.
And that distinction, the strongest possible MFA, is vital because standard app-based MFA, like TOTP and even SMS MFA, are known to be vulnerable to advanced phishing attacks.
They are. Real-time phishing attacks, often called man-in-the-middle attacks. Phishing kits are so sophisticated now they can proxy a login session, capturing the username, the password, and that one-time MFA code in real time.
Which is why the absolute security best practice for high-privilege admins, the people who could literally shut down your company,
is to require hardware security keys.
How do hardware keys like a Titan key or a YubiKey defeat that kind of phishing attack where an app-based code might fail?
It's all about cryptographic verification. When you use a hardware key, the key itself verifies the origin of the login request. It actually checks the domain URL.
Oh, interesting.
So if you're being phished on gcp-login.xyz instead of the legitimate accounts.google.com, the hardware key refuses to release its cryptographic signature. The domain it sees doesn't match the origin that was embedded during registration.
So the phisher gets nothing.
The phisher gets nothing, even if they trick the user into clicking the link. For admins, hardware keys are completely non-negotiable.
So we've built the foundations of identity and process. Let's dive into Section 4, where we apply true surgical precision using the advanced features of GCP IAM. And we'll start with IAM conditions, which moves us from who can do what to who can do what only when.
IAM and conditions are incredibly powerful. They're powerful because they introduce context. They let you define access based on attributes that are outside of the core identity or the resource itself. It's the difference between granting a role forever versus granting it only when specific environmental factors are met.
What are the primary contextual attributes we can use to filter or constrain access with these conditions?
We rely on three main categories. There are time-based attributes, so limiting access to a specific period. There are resource attributes, filtering based on the resource's metadata, its labels, or its name. And then there are network-based attributes, ensuring the user is coming from an approved IP range.
Let's start with time-based. How can we use this to minimize the exposure of, say, temporary roles?
This is perfect for vendor or temporary contractor access. For instance, you could grant a vendor the cloud storage object viewer role, but you attach a condition that says the access is only valid between October 1st and October 30th of this year.
And when that time expires?
The moment the time expires, the IAM binding becomes inactive. You don't have to rely on an admin remembering to go in and manually revoke the permission on the 31st.
Now for resource attributes, this is where the power of good tagging and naming conventions really comes into play.
Absolutely. Think about managing your dev and test environments. We can grant a developer the compute instance admin v1 role, but only if the target resource matches the expression resource.name.starts with def.
So if they try to touch a production server,
If they attempt to perform an admin action on a VM named prod AP server zoo5, the condition fails the check and the permission is denied. It enforces that logical separation based purely on metadata.
the hypothetical scenario of vendor data access is a perfect illustration of this, filtering access right down to the data's metadata itself.
It shows you the depth of control you have. If a compliance rule says a vendor can only analyze public data from a specific year, you use an IAM condition that filters based on the object's creation timestamp. You can specify something like resource.creation timestamp 2024-01-01T0000000000.
So they can only read objects created before the current year.
Exactly. It provides verifiable compliance right down to the millisecond.
And finally, network-based constraints. These seem critical for securing databases and sensitive APIs.
They are. For services like Cloud SQL or Bigtable, you often want to restrict access not just by who the user is, but where they are. You can use a condition to grant a developer Cloud SQL editor access, but only if their originating request IP address falls within a specified corporate VPN range.
So if they're at a coffee shop on public Wi-Fi, they're blocked.
Even with the right credentials, access is blocked. This massively reduces the risk surface for remote attacks.
This entire structure of permissions and conditions, it all relies completely on understanding the flow of authority. So let's move to hierarchy and inheritance, which is really foundational to how GCP applies every single one of these rules.
The GCP resource hierarchy is the ultimate rulebook. It's this rigid top-down structure. You have the organization at the very top, which cascades down to folders, then to projects, and finally to the individual resources like VMs and buckets.
What is the fundamental, non-negotiable rule about how permissions flow through that structure?
Inheritance is strictly additive. Any policy binding, any role you grant at a higher level in the hierarchy is automatically and completely inherited by all resources nested below it.
So if you're a folder admin,
If you are granted a role at the folder level, you possess that role for every single project within that folder.
okay, this brings us to the famous inheritance trap. I think anyone who's managed permissions manually has made this mistake at least once. Can you detail that failure of trying to restrict an inherited permission?
The trap works like this. You grant user X the organization viewer role at the folder level because they need visibility across all the projects in that folder. Later, you realize Project A is highly sensitive and you try to block user X from seeing it. So you go to Project A's IAM policy and you explicitly remove their role there.
And why does that fail?
It fails because permissions are additive. The inherited higher-level grant always takes precedence over the removal attempt at the lower level. You cannot deny an inherited permission by simply omitting it from the child's policy list.
So user X still has viewers on Project A.
They retain the organization viewer role for Project A because the grant was made higher up in the hierarchy. To truly restrict them, you have to either remove the grant at the folder level or use the more advanced specialized IAM deny policies.
Understanding that additive flow is so crucial for preventing accidental overpermissioning. Now, policies are dynamic because organizations are dynamic. That leads us to the critical need for regular auditing and review.
Policies are like code. They decay over time. People change roles, projects are sunsetted, vendors finish their contracts. If you set a perfect least privilege policy today, policy drift means you will have a security gap within 3 months unless you are continuously monitoring and adjusting. It's just non-negotiable.
What tools can help us automate and smarten up this monitoring process?
The single smartest tool GCP provides for this is the IAM recommender. It uses machine learning to analyze a person's actual usage patterns over time. It looks at which permissions they actually invoke and which ones they don't.
So it's not just checking the IAM binding, it's checking the audit logs to see what they did. Give us a detailed example of the recommender in action.
Okay, a user, Jane, was part of a data migration project 6 months ago, and she was temporarily granted the broad BigQuery admin role. The recommender analyzes the last 90 days of her activity and sees that she hasn't executed a single BigQuery.datasets.create or BigQuery.jobs.create operation.
So it flags the unused role.
It proactively flags her unused role and generates a specific recommendation. Remove BigQuery admin from Jane, suggested replacement, BigQuery viewer. This moves us from reactive cleanup to proactive risk reduction.
And when we need to investigate actual activity or maybe unauthorized attempts, where do we look?
You need comprehensive logging, and for that you go to cloud logging. We have to distinguish between two crucial types of logs here. Admin activity logs track control plane operations, creating a project, deleting a VM, changing an IAM policy. Those are always on and retained by default.
But for security investigations, you often need more.
You need data access logs. These track access to the actual data payload, reading a cloud storage object, querying a BigQuery table, or accessing a Cloud SQL database.
And why are data access logs so important?
They're configurable, but they are essential for detecting data exfiltration attempts. If you see a service account that suddenly reads objects from your sensitive financial bucket 10,000 times overnight, but it normally only performs 5 reads, the data access log is the evidence you need. Auditing means setting up alerts on that anomalous activity.
Let's close out this section with that painful counterexample that audits are designed to prevent.
Right, the classic audit failure. A third-party security contractor is granted the highly elevated Cloud SQL admin role for a 2-week security assessment. The project ends, the contractor leaves, but 6 months later, their user account, now dormant, unmonitored, and still holding that high privilege role, is still bound to the project.
And that account is now a high-value target.
A high-value, low-risk target for external attackers because it will be overlooked by standard user audits. Regular auditing closes that window of exposure.
That sets us up perfectly for Section 5, creating the absolute hard guardrails using organization policies, and then how we debug when things inevitably break.
This section is a bit of shift in focus. We've established IAM, which is who can do what. Now we talk about organization policies, which answer the question, what can be done, period.
So what's the key distinction between IAM and organization policies?
Organization policies are preventive controls. They act as hard vetoes or global constraints that you apply at the organization or folder level. And they cannot be overridden by project owners or even most IAM roles below them.
So IAM grants capability, but organization policies restrict capability.
Exactly. If an organization policy says you cannot create this resource type, then no amount of IAM permission will allow it.
This is where we enforce that Wi-Fi best practice we talked about. What's the single most critical constraint we should be applying at the organization level to enforce keyless access?
The absolute most critical one is constraints.disable service account key creation. When you apply this at the organization root, you instantly prevent anyone, even a new project owner trying to work around the system from creating those insecure, long-lived service account keys.
The JSON file.
The JSON files.
That's incredibly powerful. What happens when a project owner tries to circumvent that constraint?
They get an immediate policy violation error. The constraint acts as a global, non-overridable veto. It forces the use of more secure methods like workload identity federation or managed identities, preventing that massive key exposure risk across the entire enterprise.
Are there other organization policies that help prevent, say, accidental data leakage?
Yes, the constraint for domain-restricted sharing is vital. In any enterprise environment, you never want data to accidentally leave the corporate boundary. This policy ensures that resources like shared VPCs or BigQuery datasets can only be shared with principals whose identities belong to a specific list of approved corporate domains.
So it prevents sharing resources with unauthorized external emails like public@gmail.com accounts.
Exactly. It's a crucial data egress prevention guardrail.
Now, we've built this incredibly complex, granular structure, but no matter how careful we are, the operational reality is this. Someone is going to get an access denied message, and tracking down the source of that denial across folders, projects, and conditions can be a nightmare.
It is the single most frustrating aspect of cloud security. Manually tracing that permissions hierarchy is nearly impossible, which is why the policy troubleshooter is an essential operational tool. It just eliminates all the guesswork.
Walk us through how it works. What inputs does it need, and what does it tell the user?
The troubleshooter needs 3 inputs. 1, the principal, the user or service account getting the denial. 2, the resource they're trying to access, the specific VM or bucket. And 3, the action they're trying to perform, the specific permission, like compute.instances.delete.
And what's the output that saves us hours of manual work?
It visualizes the entire decision flow for you. It shows every single binding, all the way up the hierarchy, from the resource, through the project, the folder, to the organization. It clearly highlights which policy grant is enabling the access, or if it's denied, it pinpoints the exact binding that's missing the permission.
And it can handle more complex cases, too.
Oh yeah, even more complex things, like whether a specialized IAM deny policy is actively vetoing the grant, maybe overriding an existing owner role.
Can you give us a complex debugging scenario where the troubleshooter would be mandatory?
Okay, let's say a developer reports they can't start a VM. You check their project's IAM, and they clearly have the compute instance admin role. The troubleshooter might reveal that while they have the admin role, there's a folder-level IAM condition in place restricting access to VM resources that don't have a specific label.
And the developer forgot to apply the label.
The developer failed to apply the mandatory label. The troubleshooter will highlight the condition that caused the veto, which is something you would never find just by looking at the role binding alone.
To bring this all together, let's synthesize these best practices into one cohesive deployment plan for a new secure data project. Let's call it Analytics Prod.
Security by design.
Yeah.
Okay. Step 1. Establish identity consistency. You sync all your users and groups using GCDS from your existing Active Directory to Cloud Identity. This ensures immediate revocation if an employee leaves.
Step 2. Non-human access and enforcing our keyless rule.
Right. You create highly specific service accounts for your critical automation, like ETL pipelines. But crucially, before you use them, you make sure the organization policy disables service account key creation is enforced. This forces those pipelines to use managed identities, or WIF tokens, eliminating static keys from day one.
Step 3. Applying PolyLP to the users and the non-human identities.
Okay, the data scientists, they need specific, limited permissions. So you grant them BigQuery job user so they can run queries, and BigQuery data viewer to see the results. And you apply this at the specific data set level, not the whole project. The ETL pipelines, which only drop data into a landing area, they get the narrowest possible role. Storage object creator for that one ingestion bucket.
And finally, applying the global guardrails we just discussed.
You apply the necessary organization policies at the folder level where this project lives. Primarily, you ensure domain-restricted sharing is active. This guarantees that none of your valuable analytics datasets can ever be accidentally shared with non-corporate accounts. It secures the data perimeter right from the start. This holistic, layered approach is really the only way to achieve true cloud security maturity.
This has been an incredibly deep dive into the architecture of GCP IAM. To quickly summarize our key takeaways for securing your cloud environment. The principle of least privilege isn't optional, it is absolutely foundational, and it requires surgical precision. For non-human access, workload identity federation is the secure standard. It bypasses that static key risk. The GCP hierarchy dictates that permissions are additive, meaning you have to audit those inherited roles very carefully.
Absolutely.
And finally, organization policies provide the critical, unoverridable guardrails you need to prevent systemic mistakes across your whole organization.
And just remember that security is a continuous process. It's not a destination. Even the best policy requires the diligence of the IAM recommender and cloud logging to ensure that today's best practice doesn't become tomorrow's vulnerability.
We have spent a substantial amount of time establishing who can access what, the identity and the resource boundaries. But within a complex environment where you have multiple projects, different VPCs, and a mix of human and non-human identities, those resources and identities need to communicate with each other.
They have to talk to each other to perform their functions.
Exactly. We've secured the front door using IAM, but now we have to secure the internal hallways and the external communication channels. So as a final thought for you, the listener, we challenge you to consider this. How do these different identities, VMs running ETL pipelines, developers debugging databases, service accounts exchanging tokens, how do they communicate securely between resources and between projects without exposing sensitive data to the public internet or to unauthorized internal networks?
We've established the access rights. Now the real question is the security and privacy of the network connection itself.
And that logical leap, securing the communication path, is precisely what sets us up for our next major discussion. Deep diving into VPC networking, private service access, and securing all egress points. Something to mull over until our next deep dive.
A perfect transition. Thank you. This was a great discussion.